This is Jamin Rader, studies climate science at Colorado State University under Elizabeth Barnes, and did a practicum at Pacific Northwest National Laboratory in 2021, and is going to speak to us about a very interesting topic involving climate and also interpretable AI, and I'm looking forward to that. It's all yours.
Hi. So I am so thankful to be going Monday because I get to get this out of the way. And second, because I get to use this as an opportunity to say, hey, come talk to me. Because I am super excited about climate science, I love machine learning, and I love interpretable AI. So if you're interested in any of those things, and I know a bunch of incoming students mentioned a lot of those things, come chat with me. I'll be here through Thursday. So yeah, so let's get started. So I'm talking about the intersection of climate science and machine learning. And a lot of the times when we think about that intersection, we think of climate modeling, which, as mentioned, is what I did with PNNL for my practicum. Some of you may have seen, for example, that NVIDIA is creating a completely data-driven climate model, which is AI-based. In addition, the Department of Energy's own E3SM is integrating machine learning into their physical parameterizations to improve the resolution of their climate model. So there's a lot of cool things going on in this space. I'm going to talk about something slightly different. I had a lot of projects, and I had to choose one. And so hopefully I've chosen something that answers a couple questions, talks about interpretable AI, and then also gets you excited about making machines think like humans all at the same time. So I'd like to start with what I've been thinking about for the last 4 years. And there's really two main questions here. First is, how can we use machine learning to improve prediction on climate timescales? We're thinking about climate predictions from like 1 year out to 10 years. And then second, how can we use machine learning to better understand our Earth system? And at the intersection of these, as I mentioned before, I have interpretable machine learning. And interpretable machine learning is the idea that we have a machine learning algorithm that is also providing its own explanation. And this is a little bit different from explainable AI that a lot of people might be used to: LRP, Deep SHAP, LIME, lots of those fun terms. Because those techniques are usually using an algorithm to explain a deep neural network after the fact. This is actually building it into the model. And the reason we want to do that is because some of the research I've done that I won't talk about today, but I'd be happy to talk about one-on-one, has shown that these explainable AI techniques don't always tell us what we think they're telling us, and building it into the model might be useful. So these two questions and this concept all come together in this preprint that I have. You don't have to scan the QR code here if you're interested in it. It's optimizing seasonal-to-decadal analog forecasts with a learned spatially weighted mask. I'll have the QR code at the end. And this is work I've done with my advisor, Libby Barnes, at Colorado State University. So I want to start off with a little bit of a background on what seasonal-to-decadal forecasting looks like today. And the state of the art is using initialized climate prediction systems. And the concept is pretty simple. The application is difficult. But the idea is that we initialize a climate model with observations, we iterate the model forward in time, and then we make a prediction using the model's final state. The idea being we've given it the predictive information that we have today, so it should be able to resolve our atmosphere and ocean more or less moving forward. So there are two main issues with this. The first is initialization shock. A lot of people like to say climate models are useful, but not perfect, and this is a great reason why. While climate models are telling us a lot about how the Earth system works, the climate model's phase space doesn't look exactly the same as the observed phase space. So you can end up in a situation where you've initialized your climate model, and because you aren't in the space it really understands, it can kind of do some wacky things that are a little bit non-physical for that climate model. That kind of acts to degrade the predictable information that you have that's actually going to help you make a climate prediction, climate forecast going forward. And because climate forecasts are so hard, any loss of information to that is kind of a big deal. And to the same point, we have climate model drift, where as this model is iterating forward, is going to pull those observations back to its mean state, which isn't helping us make a prediction on how our climate's going to vary moving forward. So the way we are approaching this is through a data-driven approach, as you might have expected, considering I've talked about ML. And specifically, we're using a technique that has been around forever. In fact, this was some of the earliest weather forecasting was earliest weather forecasting was analog forecasting. And so the premise is that if two climate states look similar initially, they'll continue to evolve similarly. So in application here, we're going to find a state in a climate model simulation that looks like the climate state we're interested in, for example, observations. This is called an analog, and we're going to make a forecast based on how that climate model analog evolved. And someone referred to this, I can't remember the paper, I have it in the citations, but someone referred to this as a poor man's initialized prediction system, because that's exactly what we're doing. We're finding something that looks like our observations without being constrained to actually running a model. So I'm going to talk about this in the scope of the North Atlantic sea surface temperatures. North Atlantic sea surface temperatures exhibit decadal variability. They're associated with a number of things that impact humans in weather and climate, including the Asian summer monsoon strength, Atlantic hurricane frequency and intensity, as well as northern hemisphere extreme precipitation and drought. So this is a region that can be used to make long-term climate forecasts. And our task here is, given an initial global map of sea surface temperature, can we predict how the North Atlantic sea surface temperatures will evolve over the next 1 to 5 years? So this is what it looks like in practice in this work. Here we're using the Max Planck Institute for Meteorology Grand Ensemble. It has just tons of information, a number of different climate model runs. We're doing this in a perfect model setup right now. So instead of using observations and predicting for observations, we're actually substituting the observations with climate model data. So we're actually making a climate model prediction for climate model data. This still teaches us a lot about our Earth system, and one of the things I'll talk about later is that we're going to try to push this towards operational use on observations. So the way this works is, if we have a state of interest we're interested in, seeing how it evolves over time, we have tons of climate model information, which all could be used as potential analogs. If they look similar to our state of interest, we can use them to understand how that state of interest will evolve. We identify the potential analogs that look really similar, and we use how those potential analogs evolved forward to make a prediction about how the state of interest will evolve. Pretty simple. So there's 3 steps to this. First is getting that state of interest and the library of potential analogs that you can use to make these forecasts. Second is determining which maps are the most similar, and the third, actually making the prediction using the best analogs. And the big question that we have here is, how do we define most similar? So there are some ways it's traditionally been done. For example, we could compute a global mean squared error. Take 2 maps, see if they look the most similar globally, and then use them to make a prediction. But for a problem like predicting the North Atlantic, we don't expect that everywhere in the globe is going to be important for determining how the North Atlantic evolves. The second way you might approach this is by computing a regional mean squared error over some known precursor region. For example, in this case, we could just look at the North Atlantic and say all the maps that look the most similar to our state of interest in the North Atlantic are probably going to evolve similarly. But there are still some issues with that, namely that it requires that we know the precursor regions before we do this. And in this case, we don't actually know that the North Atlantic is the best prediction region for that North Atlantic area. Maybe the Indian Ocean, maybe the Southern Ocean are all kind of teleconnecting and feeding back to determine how the North Atlantic is going to evolve. It also assumes that all grid points within this region are equally important, and as we'll show in a slide in a few slides, that's not necessarily the case. So the way we're defining most similar here is still pretty simple. It's computing a spatially weighted MSE. So every single grid point in each of these maps is going to be associated with a weight. A larger weight indicates that it's important that that grid point is similar between 2 maps for the North Atlantic evolving similarly. If it doesn't have any weight, it means that we can completely disregard any similarities or differences between our map and an analog in making a forecast. So how do we obtain this weighted mask? And this is where interpretable machine learning comes into play. So directly using machine learning to learn which images, which analogs are going to be the best is actually an incredibly difficult task. It would be very computationally expensive. So here we're training it on a proxy task. This interpretable neural network architecture, which I'll go into in a second, is tasked on a slightly different problem from the analog problem. It's actually tasked to predict how similar or different two maps will evolve in that region. The idea, however, is that en route to making this prediction, it must learn an optimal spatially weighted mask, which tells us information about how the North Atlantic is going to evolve. So this is a kind of a look at the architecture here. It's a really simple architecture. This is intentional. I think a lot of the times we try to make architectures really, really complicated. And if we just kind of scale it back a little bit and make an architecture that thinks the way humans do, it can be really beneficial for doing good science. Not to say that complicated architectures aren't. There's lots of good stuff. Yeah, ResNet's important. But so in this case here, we have two input samples coming in. They're both multiplied by a mask of trainable weights. An MSE is computed, and then dense layers map that MSE to a predicted difference in the evolution of the target region. So in this case, the main way that it can learn the difference between how two maps are going to evolve in the North Atlantic is this map of trainable weights, which we can then freeze and use as a mask for the analog problem. So here's a look at the weighted mask for predicting the North Atlantic there, which is shown in the box. And we can see that there are kind of two main regions that pop out as being important. These are important precursor regions that kind of give us information about how the North Atlantic is going to evolve. And we can kind of see this area here off the east coast of the United States and this area off the coast of Greenland. And this is, I think, particularly important because this slide here not only shows us that we can use kind of an interpretable neural network to improve our prediction skill, but we can use it to actually better understand our Earth system. Here's an example of the best analog for one sample state of interest. On the left, we have sample 223, a random sample from our testing set, and its best analog. And when you look at these maps, you'll notice, first off, some regions in the two maps look very similar, specifically this North Atlantic region. Lots of other areas of these two maps look extremely different, such as the North Pacific. But because the North Pacific isn't important and the North Atlantic is, we can see that once we've weighted these two maps, we see they look very, very similar in the regions that are important for climate predictability. Here's a quick look at some of the predictions. In black, we have our predictions. In blue, we have truth. We can see that these are covariating pretty well. They're doing a pretty good job of capturing predictions. I think the next question is, did we actually do a better job than our traditional analog prediction techniques? And I wouldn't be presenting this work if we weren't. So that's kind of a heads up. So our results are here in gold. That's the weighted mask analog. A higher skill score means better. 0 means climatology. And our technique performs quite a bit better than if we were just looking over the North Atlantic, as some papers have done in the past, or looking over the entire globe. And as a comment regarding HPC is that this is an embarrassingly parallel problem. I love that term. The most computationally intensive step for this work is actually computing the MSE between the tens of thousands of maps that you have. Super easy to put in parallel. In our case, this decreased the time by 1/7. Different people, if you had better hardware, you'd be killing the time quite a bit more. Looked away for a second, it switched on me. OK, so some takeaways here. First is that interpretable neural network architectures can be used in conjunction with traditional prediction methods to improve climate forecasts. And that in addition to improving forecasting skill, these methods can highlight precursor regions for climate variability. Looking ahead, we're asking two questions. Can we apply this method to observations to make real-time seasonal-to-decadal forecasts of climate? And this may require some extra data from many different climate models to try to get a lot of patterns that might all represent how observations, our observed Earth system actually works. I'll be working on that with Martin in our group. And then can we extend this method to sub-seasonal timescales? And I'll be working on that with Jacob. And one of the things we'll have to think about is how do we, with such noisy data, actually do that problem? It's very, very difficult. You need a lot of data, and you need a lot of computer resources. So I'd love to finish this talk with some acknowledgements. First, the Barnes Research Group has been an incredible group to be with. Conversations with each and every one of these individuals make my day and make my science better. So I just wanted to throw them up on a slide here. And then, of course, a huge thank you to DOE CSGF and Krell for all the support the last few years. I feel like I've gotten to think about data science in a very different way because of the conversations I've had at these meetings and the support I've had. So with that, I'll end it, and we'll take some questions.